studio experiences organized by Amity University, Chhattisgarh. We have had really fruitful 3 days until now. We have had different lectures, and all the lectures were very good. We have gained good response by all participants in all the lectures, and today also we expect your active participation. And I hope that you gain and learn a lot from the lectures today as well. We have with us our expert for the day, architect Anubha Astikar, ma'am. Ma'am is a senior architect and senior sustainability specialist. She is a graduate from NIT Raipur, and then she has done her master's in sustainable architecture from CEPT Ahmedabad. She is currently associated as senior associate with an MNC based out of Gurgaon. Prior to that, ma'am was a senior sustainability expert with Integrative Design Solutions Private Limited, Delhi, handling sustainable development and green certification projects. She has also created developments of guidelines for Nigeria for energy efficiency, and she has worked with Climate Smart City Assessment Framework as well. She's an active member of various societies of national and international repute that are working towards bioclimatic architecture. And she has also contributed in developing sustainable village development action plans and proposals through government schemes in various areas, especially in the state of Chhattisgarh. Ma'am, we are honored that you have accepted our invitation and you decided to give time for this faculty development program, and you're here to take this lecture. We are all really looking forward to learn from you today. And the topic for your lecture, that is climate conscious design studio, is also very interesting. We study climatology as a basic subject in our architectural curriculum. Climatology is also taken by a lot of us who are present in this faculty development program as a subject, but sometimes we are unable to translate the knowledge that we gain through this subject in our design studios. So today's lecture will be all about that, and we're all really looking forward to these two sessions today. Ma'am, now I hand over the mic to you. You can please take over.
Yeah, thank you, Nishta, and thank you so much for having me here. And I'm really, I'm feeling happy that so many participants have joined, and I'm looking forward for a really interactive session. So first, I just want to say that it is more of an interactive session. We are all learning, we are all here because every day something or the other things are changing, and climate change. And when we talk about climatology and applied climatology and all, it is all it's not stagnant. It has every other day we are coming up with a different issue, and we are finding to mitigate those challenges. So I really look forward for an interactive session, and thank you all participants to join. And I'm just giving you a heads up, I might be asking questions in between, so be prepared. And I just to understand, not to test your knowledge, just to understand that my lecture is not boring you and you all are not sleeping. So maybe in between when I ask questions, you can type it in the chat box. And if there is a yes or no answer, you can just type it in the chat box, and Nishta will take a follow-up for all the responses that we have received. So I will just present my screen, and then we can start. Let me know once you will be able to see my screen. I am pausing my video for some time because then I'll face a bandwidth issue. Are you able to see it in a full screen mode?
Yes, ma'am.
Yeah. So as Nishta has mentioned already, the session is about climate conscious design studio. I have rephrased it a little bit. I'll be talking more about the applied climatology for high performance building design. So here only, with this topic only, I think the lecture start that we will be discussing about the climate conscious design and the applied climatology, because we all know that we have studied climatology, we have all been studying climatology, but how to apply it. And then what exactly is applied climatology? So basically, if you have all these questions and if you have all these, queries in your mind when you want to understand the performance of the building, you want to understand the energy analysis, like whatever you have designed, how is it translating into the performance? Suppose if you're designing that, the building will be in a way that it will be consuming less energy. So how will you actually calculate it or quantify it? And how will you actually understand whether the wind directions that you have planned for is actually, ventilating the entire building or not? So if you have all these type of questions in your mind that you want to learn and understand, there comes the applied climatology. Whatever your theoretical experience or learnings you have to apply it in the practical field, is where we say that, the applied climatology comes into the picture. So, as per my understanding, when I got an invite from this, I just wanted to understand what will be the objective of the lecture. So, the objective of this entire lecture is to, understand the need of the industry and to upgrade yourself. So, it's not a theoretical lecture where, we'll be talking about what is the CDD, HDD, what is the azimuth angle, or how the sun rotates, and how are we getting the sun, or from which direction we are getting the sunlight from. We all know about that. The idea is to based on your understanding of climatology, what you can do in the industry. So suppose we are, like, I am an architect and I am from the architecture background. I suppose most of you are from that background. So it's not limited to the conventional architecture these days. We are, evolving more, and we are trying to understand the design aesthetic, performance aesthetic, and we are trying to compare both. We are trying to catalyze our informed decision making, and also to understand how the integrative design process will work. And we need to learn and we need to understand the market demand for all the analytical methods that the design professionals are using. So basically, this lecture, as per my understanding, the objective of this lecture is to understand the need, to prepare you to understand the need of the market, and to become a pro version of yourself by taking some kind of courses. Maybe you might, I'll be in the end of the session, I might be telling you about few of the courses and few of the tools that we are using it in the industry, that will help you develop professionally and to learn and evolve more in this profession. So the idea, so what is the difference between teaching and training? So just when in teaching, you know the theory, you know the knowledge, you know all your tools. But in training, you have to understand the practicality of it. You need to develop your skill, and you have to understand what is the right tool to use it for the specific issue. So for example, if you see a Swiss knife here, you have lot many tools here. As per your knowledge of climatology, you might be knowing everything, but how to apply it is what is important in the field. It is not necessary that all your knowledge will be applied, but yes, the specific knowledge will be applied to the specific area. Same teaching and versus training. You have theory knowledge and a comprehensive understanding of everything, and while teaching, you have the ideal world situation. But during the training, you need to understand again practicality, skill, specific, and then the real world. So many authors have said, as I've quoted here, in theory there is no difference between theory and practice, but in practice there is. You might be, in theory you might be imagining that there will be a utopian situation, your design will work like this, how you have planned for. When I understand, when I was a student, I used to make different kind of arrows, and my teachers used to tell me, okay, tell me how the wind flows, and I used to make different colorful arrows, blue, red, cool wind, hot wind, warm wind. But in actual design it doesn't work that way. So that is what is the understanding that we need to gain to upgrade ourselves in this industry. So what is our journey of upgrading ourselves? In a brief, it's like, from basic, you need to develop a smart tool understanding and becoming a pro version of yourself. Like we keep doing, as I've said in the beginning as well, it is not, we all know that we have all the smartphones and all, and we keep upgrading the smartphones with different versions of its operating system. So if there is an iOS 14, then it will be, iOS 14.1 will come, 15.1 will come, iOS 16 will come, 16.1 will come. So we need to keep upgrading ourselves based on the market need and the demand. So what is the cross bridge between the building design and its performance? So it's from, analyzing the design and making it a more practical version of it. So if you see on the left hand side, I am showing how the sun path will be, how the wind direction will be. And on the right side, it is the actual design, how it works actually, how the sun, how we are going to get the daylight inside the building, how are we going to see the performance of the daylighting, etc. Similarly, for the wind flow analysis, as I've said, we have designed everything with a very beautiful master plan and all, but in reality, it actually we have to quantify that actually where are we getting the negative pressure, positive pressure, and how are we actually, orienting our building in terms of, in terms of, wind direction and the intensity of the wind, and where can we get more of, naturally ventilated, like more advantage of the natural ventilation inside the building. Heat gain analysis, as we have seen, we used to, design a building in a way that, okay, sun will be at this angle, then it will be at this angle, and this is how much of sunlight we are getting. But actually, how are we going to understand how much is the heat gain analysis is where we need to upgrade ourselves and learn more tools to understand the impact of heat gain and to quantify it basically. So with this, I'm going to start my session. So yes, previous few slides were just to give you the hang of what is this lecture gonna be. And now with this, I'm gonna start with the understanding of today's topic. So starting with climate change, we all know climate change is popularly used term now, and nowadays it is impacting all the industries that I have quoted here, whether it is agriculture, forestry, fishing, healthcare, governmental services, everywhere. We all know there is a climate change and it is impacting us a lot. And what is the cause of climate change? All these greenhouse gases, which are, which we are emitting it in the environment, and that is the effect, and that is causing the climate change effect. And can anyone tell me in the chat box, maybe Nishta, if you can just, tell me who has given the right answer, which greenhouse gas is the major stakeholder to contribute for the climate change? We have so many gases here: methane, carbon dioxide, carbon monoxide, nitrogen oxide, and all. Can anyone tell me which gas is the major stakeholder of climate contributing to the climate change? Any answers? Very good. Yes, CO2. So why CO2? Because if you see, out of all the CO2 greenhouse gases, CO2 is the major stakeholder because it remains for a longer time in the environment and its phase out time is very long. So because it is there very long and is the major stakeholder and contributor, we need to understand that how to limit our emission of carbon dioxide in the environment to reduce the impact of climate change, or not to reduce it, to mitigate the impact of climate change. So if you see the reason of, if you see how the atmospheric CO2 fluctuation was, so from ice age till 19th century, like 500 years ago, from ice age till 19th century, we have the fluctuation of CO2 from 180 ppm to 280 ppm. Okay, but in current post-industrial revolution, if you see the fluctuation have it has increased so much that it has increased from 1.5 times of carbon dioxide emission to the more than, like, it's like almost 100 times. The projection is like that. So we understand why is the need, why do we need to mitigate the impact of CO2, and we need to understand how to reduce the CO2 emission in the environment, is because we are contributing to a lot of emission of carbon dioxide in the environment, and that is causing a real problem for us, and it is going to cause a real problem for our future generation as well. So what is the global warming effect? So we all know this. So it's in a very simple term. It is like when we have the, when we have the radiation coming through, and then if it is getting reflected back, it is the normal concentration. But if it gets trapped inside the, outside the Earth environment, then the concentration becomes high, and then it causes the warming effect. And why does it become trapped? Because of all these greenhouse gas forming a layer which is not allowing the radiation to go back, dissipate back in the universe. So basically, because of that, this entire radiation is getting trapped, and we are getting a higher atmospheric concentrations, and which is actually warming the environment. So now, so since we have talked about CO2 emission and all, we need to also understand how what is causing these CO2 emission. So if we see our situation, our energy generation and consumption scenario. So if you see, our major energy generation is from thermal plants, like almost 70% of the electricity we are generating from the thermal plants. And then if you look into the electricity consumption, how we are consuming the electricity in various sectors. So after industry is consuming 42% of it, building is contributing 33% of the electricity consumption, then agriculture and different sectors are consuming the rest of the amount. But if you see, we as an architect have the major role to play, because building contributes to 33% of electricity consumption. And if, as as a response, if with our design informed design decisions and responsible design, if we can reduce the carbon dioxide emission in this sector, we are going to make a big change in the environment. And if I just wanted to show this simple calculation, if we are consuming 1 kilowatt hour of electricity, we are indirectly contributing to 0.82 kgs of CO2 emission in the environment. So now, can anyone tell me, like, what is the average load that we get sanctioned for a single residential unit to for the electricity, like for the connected load and all? Any idea? I mean, how much of electricity load that we take for one residential unit? Like, if anyone has seen the electricity bill and knows the load. So usually it varies between 5 to 7 kilowatts, kilowatt hours, or it varies between that range. So we are actually contributing that much of with one single unit, we're consuming that much, and into 0.82 kgs of CO2 emission. And then if you can just go back and check your electricity bill, you will be actually able to understand that how much of electricity that you are consuming and indirectly emitting the CO2 emission in the environment. So what is the forecast? So we all know that electricity consumes more, the building sector consumes more electricity, and by 2060 we are gonna build twice the building stock, as is yet that is what is yet to come. Okay. And from if we will not be making and with current rapid growth situation, with current construction trends that is happening, if we are building and constructing an inefficient building or a carbon intensive building, then it is going to be a huge problem for us in future. So what we need to do is, we need to understand that if you see India's floor area addition, by in just few more years we'll be developing almost like double the construction, we will be doubling the construction industry in like just few more years. So we need to understand where do we need to pitch in, and how do we need to design our current future building stock, and how to improve your existing building stock to mitigate the climate change, to mitigate the negative impact in the environment. So what we need to do is, the need of the hour is, we need to seek, improve, and alter, even disrupt. We love to design and redesign. I have quoted here, the buzzwords today are innovation, disruption, and both are considered as positive. But we need to ask ourselves these questions, that if we are not going to design it in a conscious way, where will we find the resources to build new housing, and where will we find the energy to maintain it? And how can we design and redesign? Responsibility should be the question in which we'll be brainstorming, and what should be the guiding principles. So from here, I just want to talk about what should be the underlying principle with which we can have a conscious or a climate responsive design, or let's say design has to be in a way where we can contribute more as a, to the industry and making an informed decision. So we know we are not just designing for the sake of designing. We need to design anything for a purpose to meet a need, and the design of particular building has to be to provide comfort and well-being to the occupants in a new way or in a better way. So we need to achieve a goal and make a statement. We need to define the three P's in the integrated design process: purpose, participants, and process. And then we need to ask ourselves this question: that what are we trying to achieve? Who should be involved as a participants, or like in the occupants, and who will be the stakeholders for the industry, and with whom will be aligning, and how can we try to deliver it? Like the process, like we need to understand that whether we will be designing it in a efficient process, the whole construction process is efficient or not. So we need to understand how can we try to deliver it. And then way of thinking should be, if we cannot measure it, we cannot improve it. So there's something when we need to understand that how to quantify our design. Like if we are having a good understanding of building physics, engineering sciences, then we'll be able to quantify it, and we will be able to do a quantitative analysis. And then we need to think creatively also, where and there our creative design process, our design gets involved. So the conclusion of this particular the background of design principle is that we have to have a mixture of the science and art as an integrated design process to develop our designs, to make all the design decisions, and that's how we'll be able to take the informed decision for making any design. Moving forward, so what is the purpose of, as I've talked about purpose earlier in the previous slide. So what is the purpose of the building? To provide occupant comfort, which are like providing in terms of thermal comfort, air quality, visual comfort, and acoustic comfort. What are the physical process that happens when we design a building, and what are the physical process that that describes, or let's say that defines the comfort of the occupants? Is the heat transfer, moisture transfer, light transfer, sound propagation, and all. And we all are not going to the basics of it, that we have this three process of heat transfer inside the building: conduction, convection, and radiation. So we all know that, so I'm not going to the basic of it, but these are the physical process based on conduction, convection, and radiation that happens, which actually defines the thermal comfort of the occupant. Hello. Yeah. So so we all know that the thermal comfort and everything will be, actually it can be designed properly by optimizing the building envelope. And when I say building envelope, we need to have a proper wall design, roof design, fenestration design, and foundation, so that we can achieve the required thermal comfort inside the building. And what are the active systems that those are which are involved to achieve the thermal comfort are the HVAC system, artificial lighting, etc. Then understanding the energy consumption scenarios in the building. If you are not going to in much detail into it, just wanted to show that we have already discussed that building contributes to 33% of electricity consumption, whereas how is the distribution of energy or electricity consumption, energy consumption in any building? So I'm just taking a typical case of commercial building. If we see, 55% of the energy consumption goes in air conditioning, like heating and cooling the building, and maintaining the proper thermal or introducing the proper comfort requirement of the occupants. So that goes, it takes 55% of the energy. Then it takes 25% of the energy to design a proper lighting, and then internal loads 15% and other loads 5%. So we need to understand that if we will be able to optimize the air conditioning and lighting loads in any particular building, it will be easy for us to reduce the electricity consumption or the energy consumption, which is indirectly translating into the reduction of CO2 emission in the environment. Now, why is the need of energy efficiency? Now, here I'm trying to, I'll pause here. I'll just give a basic definition here, that we are trying to hold the increase this is mentioned in the Paris Agreement, that we need to hold the increase in the global average temperature to well below 2 degrees compared to the pre-industrial levels, and we need to pursue our efforts. So it is mentioned that we need to be below 2 degrees Celsius, but we need to pursue and make some efforts to limit the temperature increase to 1.5 degrees Celsius above the pre-industrial level. So here what I'm trying to make you understand, because this is the question majority of the times it comes to you, and I'm sure you might be answering, you might also be thinking it's difficult to answer this question, because many a times when people come to you and they ask, okay, building energy efficiency, what you need to do is just simply install renewable sources of energy, or just simply install solar panels. But that's not the case. We need to understand the process of it. It is not simply just switching to our energy demand to the renewable sources of energy. We need to put more efforts in designing and reducing the internal loads of the building, and then switching to the cleaner sources of energy. So if we see the life cycle of the building and design process, so this is like, these are the basic steps that I've mentioned. We do preliminary design, design contract, detailed drawings, bidding process, then contract negotiation, and then construction process. So if you see, I've tentatively mentioned the number of months that we take, in this particular building design process. So if you see, 30% of the process will go till, if you see detailed drawings, only 30% of the process goes in designing, whereas rest of the 70% of the time goes in execution of the building. So my question is that I particularly think that this is a challenge here. We are putting 33% of the time in designing a particular building, where we are going to spend 90% of the time, as we spend, as we spend 90% of the time indoors. And let's say for 50 years, 50 to 75 years, we are going to live in that building. And for living in that building, we are just putting 30% of our effort in designing it. So the need of the hour is, we need to put more time and effort in the design stage itself, to understand and to improve the air quality of the building, to improve the thermal comfort inside the building, and the visual and acoustic comfort of the building. I hope you might have all heard about, understanding the discomfort hours inside the building, and you all might be, learning the calculation of discomfort hours during your climatology study and all. So where does it apply? We all learn many calculations, we all learn many formulas, we all know different types of analysis and assessment, but where do we apply it? So we need to apply it here. We need to apply those theories here to improve these three parameters inside the building. And how will it happen? In the initial stage, we need to understand the passive strategies, which are climate responsive in nature. We need to understand how are the surroundings of the building, how are the site specific requirements of the building, what are the materials available and all. And then we need to, after that, then we need to apply the active strategies, how to, make the building thermally comfortable, what will be the mechanical system, electrical system, and all that. But it has to be a mixture of both, and we need to put a lot of effort in properly designing a building. Like almost at least 50 to 60, 50 to 55% of time we need to spend, and we need to have an integrated process to understand that we should come up with the right design for the right situation, or the right for the specific requirement. So so the moral of this entire discussion, or the previous slides, are that we all know that during the design and construction stage, we put the human and material resources, which is called the capex, and then during the operation phase, we consume the electricity. And if we optimize the resources, the human and material resources, during the design and construction phase, we'll be able to, the capex will be increased, and then the opex will be reduced. So that is the whole understanding, to understand and to balance the operational expenses or the capex that we are talking about. So we need to have a proper balance about it. Now, coming back to the previous question that I have asked, that everyone would have asked you, ki, "ठीक है, आप, just install the solar panel, then your building will be energy efficient or something like that." But do you think that's the right process? So I don't think it is, because first we need to avoid the wastage. So if this entire pyramid, if I'll try to reduce it in a 3 step, so first we need to understand how to avoid the wastage of resource and energy consumption. Then we need to save the energy in terms of, with efficient usage of fixtures or appliances, or with building design parameters and all. And then we need to shift to the renewable sources of energy, because the more we move upward towards this the pyramid, the complexity and the investment of the parameters increases. So if you are at the bottom rung of the pyramid, if you know how to avoid the wastage, it might be a low cost or a no cost measure, but with simple habit change and all. And then if you see the middle rungs of the pyramid, if you are using the energy efficient fixtures and system optimization measures, or how to reduce the resources consumption efficiently, then it might be a medium cost or cost effective measure. And then you can shift towards the renewable and the replacement towards the clean energy system. And yes, it might be a high cost measures, but it is needed if you have to further reduce your energy demand. So now, based on this, let's roll out to the understanding of what are the main 5 verticals of a climate conscious design, because we have all understood the background of climate change, climate conscious, what is the need and where are we supposed to apply it. Now let's see what are the 5 design verticals to attain these kind of design parameters or a design of a building. So it has to be at the conceptual design stage when the project is getting launched. The idea has to be seeded there, aligning all these stakeholders relevant to the industry to add the project value and credibility of it, and to address the global causes that will be, that will improve the sustainability of the building, and it will help us to design world changing designs of building. So the first vertical is learning from the nature as systems. So we all know, we all have read about the biomimicry designs, bioclimatic designs and all, but what exactly it is? So it is from learning from the nature. You all might have seen that nature does nothing uselessly, and I have put another quote here, that humans subtly will never devise an invention more beautiful, more simple and more direct than does nature, because in her inventions nothing is lacking and nothing is superfluous. And when I say this last line, nothing is lacking and nothing is superfluous, what do I mean by this? With nature, and by understanding of the nature, we have understood the word called optimization. You might have heard it. Optimization is neither lacking of anything nor over, nor the superfluous use of anything, but the right amount and the right consumption. So that's the word called optimization, which we should learn from the nature. So as I've said earlier, nature, whatever design, whatever nature has designed for us. Like for example, let's take a ant hill example. Whatever, it's a very simple design, very basic design. Nothing is lacking in here, nothing is superfluous, but the fundamental attributes are very clear, and based on which we need to understand that how to design our building so that we are not exploiting the resources that is available in the environment. And then ask yourself, does my design lack anything, in terms of daylighting, comfort, natural ventilation? Learn from the environment, and then design something, and then try to learn from your design, that if I'm lacking anything in the design, or does my design include superfluous or useless components like wasting energy or resources. Many times it happens, like we used to put many things additional in the design just to make it look beautiful, that translates into the unnecessary consumption of resources, which might not be needed. So the first vertical is to understand from nature the how to optimize the building system. The second vertical is respect energy and resources. And why is it necessary? Because it is going to exhaust very soon. So The three parameters of resource efficiency is, we all know that we need to plan for the future, minimizing the impact on environment. We need to reuse and recover by doing more with less. And then we are supposed to optimize the resources using energy, material waste, and water in the most sustainable manner. And understanding of everything, and once you understand everything, once you have all your principles and ideologies clear in your mind, then you jump into the design process, that how to make a integrated building design. What will be an integrated design approach, combining all my understanding in terms of making and then applying it at the various stages of design, and help and all these principles and ideologies will help you make informed decision, which is what is required. Many times we design something, and in a what do you call it, in a flow of thoughts that we get during the design of any particular building, because we are all architects, we cannot restrict the design ideas coming in our mind. But we need to understand whether all these ideas are leading you towards the right direction or not, and that is where you need to take informed decisions based on how energy efficient and passive if how energy efficient and climate conscious your strategies are, choosing the suitable materials as per the site specific requirement, decreasing the dependency on the non renewable sources by orienting or designing a building in a way where if you're getting a proper lighting, if you're getting a proper thermal comfort inside the building, conserving and recycling the resources that you're going to use inside the building. So here I would like to tell you that these are the different analysis that you can do as a on your design to understand the climate consciousness of it. At the site level, you can do the site analysis where you can understand the site topography. You can do shadow analysis. You can understand the natural water resources. Then you can design to mitigate the urban heat island impact by doing the urban heat island assessment, by doing outdoor wind CFD models, which will help you in the wind flow directions and all. At the climate analysis level, you can understand the sun path. You can do the sun path analysis, wind flow analysis inside the building, form and massing analysis of the building. How whether the design of the massing of the building will be compact, or we need to make it in a different staggered way. So you have to do these kind of analysis when you're designing the building. You need to also integrate the passive design features at the design stage itself. Then coming to the building analysis level, you can do indoor CFD modeling, building envelope optimization, day lighting simulation, artificial lighting simulations, thermal comfort analysis, box modeling simulation, innovation designs, material consultation, etc. And then at the water assessment, you can do rainwater calculation, stormwater harvesting, recycling and reuse of water. And then for the waste management, you can understand the solid waste management and zero waste building design model. So all these kind of analysis, additional to what you are doing for making a design, is required for you to take informed decision. And I have mentioned few terms called simulation, daylighting simulation, building envelope optimization, and all. These can be done, which I'll be talking about in the next session. I'll be giving a brief idea of it, and we'll be sharing few links so that you can, if you want to learn the tools from there, you can do it. So these kind of simulation and analysis, it is very handy, and these days it is very easy to do, where you can develop a real-time model. Like currently you are using architectural softwares like AutoCAD or SketchUp or Revit or something, but you, as an additional understanding of it, where you are using the software to design it, there are softwares available which will help you understand the performance of the building. So if these two softwares goes hand in hand together, you become the pro. And you, if you have the understanding of using both of these softwares together, and if you have the understanding of analyzing your design in terms of both, in terms of design and in terms of aesthetic performance, and in terms of energy or resource performance of the building, then you are going to upgrade yourself, and then you are going to apply your climatology understanding in the practical field of it. Coming to the third vertical, we need to show respect for the place and people. And why I'm saying this, we need to understand the different typology of the houses. As you see here, If you see earlier days, we need to make different type of designs. Like in cold climate, we have a different design styles. In warm and humid climate, we have a different housing typology. In in the composite climate, we have a different housing typology. In hot and dry climate, we have a different housing typology. But why do we used to do that? Because we need to respect, we were earlier respecting our climate, we are giving more focus to the local environment, understanding the place and the culture of it. So if you see these examples, like, we are not building, some different type of building in a cold climate, or where it is not unnecessarily required. So if you see all these kind of housing typologies that we used to build, and it is which are actually required for the place specific requirement, we as an architect, currently what we are doing this. If you see buildings in Mumbai, if you see buildings in Gurgaon, both the cities have different climatic conditions, but a different similar type of but they're having similar type of building designs. Do you think this is the right approach to design it? No, because then what we are doing is we are creating a problem, and then we are trying to find a solution that, okay, why is my building not performing well? Why is my electricity bill so high? Why am I facing so thermally uncomfortable inside the building? So this is the problem that we have created, and then we are trying to find a solution for it. Okay, now what should we do? We should apply solar panel in it, or we should change the HVAC system inside the building to reduce the electricity bills and all. But why at the later stage? Why as an architect do we not have a responsibility to make a design in such a way that we are not dependent on the mechanical system? So this is the third vertical from which we need to understand and learn that how to improve our designs in terms of respecting the climate and the culture of the place. Then the fourth vertical is introducing an integrated approach for high performance building design. So from here it will be a little technical. I want you all to put more attention into it. So the traditional process was earlier, पहले concept design or schematic design phase में architects and designers used to come. So initial stage, architect gets involved. Design and development stage, MEP and structural engineers get involved. Then for the services and all, HVAC engineers. Then for construction stage, the project management managers comes into picture. But that needs to change. We need to have a whole system of design approach with an integrative design process. At the initial stage itself, we should have a design chariot, and at the concept design and the schematic design stage, everything needs to be fixed, everything needs to be finalized. All the stakeholders should be aligned together. They should be sitting together and telling us that, okay, these are the design requirements. And if you remember the life cycle of the building slide that I've shown earlier, then only we are going to increase the 30% of time that we were spending earlier for the design stage to almost 50 to 60%, and will be able to improve the design performance, or the resource performance of the building. So design chariot is the important term that is, you might be hearing it a lot in future, that we have the all the stakeholders involved for the building design are together and doing a sharing to understand the concept design and to finalize the concept design and schematic design of the building. So now if I show you the energy efficiency canvas of the building. So if you see, we have different aspects. We have policy for achieving building energy efficiency. And why I'm just talking about building energy efficiency, because as I've explained earlier, so energy plays a major role. Energy contributes a lot of carbon dioxide. Consumption of energy results into a lot of carbon dioxide emission in the environment. So we need to focus more to mitigate that. So there are different policies and guidelines that government have developed for building energy efficiency, like different policies and codes are there in place. We have green building and rating system guidelines in place. We have different mechanism, financial mechanism in place. We have user behavior for demand side management and design response in place. And then we have bilateral and multilateral programs to achieve the building energy efficiency. And so what should be our design approach when we do a building energy efficiency? So just this is a schematic of the whole understanding. So I would like you all to put some attention in it. So any building design So we need to design it based on if any building will be designed based on the climate, building use, and then it based on what we are, what kind of design features that we are introducing in it. And then there will be a certain load, electricity consumption load or energy consumption load that will be associated with it. This load will be for the system and the energy. This is what, so it has to be for the system, and then there will be certain energy consumption for it. So our first approach is, how if suppose we double the system efficiency? Like what we are saying, that for example, the design is in place, let's double the efficiency of the system, of whatever systems that we have applied. Let's say for example HVAC systems or electrical systems that we have applied, let's double the efficiency of it, let's put more efficient system in place. It will definitely reduce the energy consumption, but it will also increase the system cost, because we are using more efficient system. Obviously it will come with some cost, right? But it is going to reduce the energy consumption, let's say for half for now. Okay, then we are saying that okay, we need to cut the load. By cutting the load, what I mean is by designing a building in certain way that it is consuming less electricity. So basically the internal load demand will get reduced, so we are reducing the demand of it. So by reducing the demand of the electricity, the system gets reduced. The HVAC system or air lighting system that is required in the building will get reduced, and then it will cut down the energy. Okay, till here I think this is clear, because by introducing the design parameters here, we are cutting the internal load requirement, which is in term. And then if we have reduced the internal load requirement, we will be needing a reduced system size to heat or cool the building, or to achieve thermally comfortable building or the energy efficient building. And then it will reduce, and ultimately it will reduce the energy demand of the building. But the ideal situation is that we reduce the internal loads by making a design, climate conscious design, or we make a sustainable design, or by designing an energy efficient building, we are cutting the load as well. And then the reduced system that we have to meet the rest of the demand of the building, we are using the doubly efficient system as well. And that will result into more energy reduction consumption inside the building. So this is what we are supposed to do. We need to first cut the load, and then when we have already reduced our demand, then we need to put the system in place which can be efficient in nature, and then it will impact further energy reduction in the building. And then you can say that okay, your building is a high performance building. Okay, so to summarize it all, we need to put more efforts in the design strategies, and that will result into almost like 50% of the energy reduction. Then you need to put energy efficiency technologies, which will further reduce the fuel consumption or the energy reduction from 50% to 80-85%, and then use the different renewable sources of energy. Then what will happen is, so then my question, I'm asking this question again, what will happen? So when if people will ask you that okay, making energy efficient building is a very simple process, simply add a renewable sources of energy, then you can actually explain them that it is not directly switching into the system of clean energy sources. First we need to the cost effective, or a more conscious manner or approach will be to make a building energy efficient is you need to design the building in such a way to reduce the internal loads. Then you should apply for energy efficient technologies, and then to mitigate or to offset the remaining demand of the building, you can use the cleaner sources of energy. That will be more efficient approach and a cost effective approach for making a high performance building design. Is that clear? I mean, anybody has any doubt till here? Shall I move ahead? Nishta, just make sure nobody's sleeping. Okay, so I am moving ahead.
Yes, ma'am. People are actually replying in the chat box. So,
okay, great,
yeah,
great.
some are hearing, at least we can say.
Great. Okay. So then coming to the energy efficiency program, I'm not going deep into it, but there are different energy efficiency programs that you should all explore after this lecture. That what are we doing in, what are the initiatives taken by government? So for commercial buildings, we have different initiatives like ECBC codes, we have energy management information system, building passport, PAT categories, deep retrofits, energy efficient materials. For residential building, we have different schemes for affordable housing, residential building codes, low cost finance, building passport, energy management system, and standard design. So I want you all, like after this lecture, just go back and do some research, understand what the national government is doing, at the central level, then what state government initiatives are, what we are doing at the state level, what the local government people are doing to enforce it. So I want you all to go back, do some research, and understand how they are actually trying to implement and enforce the energy efficiency in the system. So I am sure you might have all seen this book. This is the Energy Conservation Building Code. This actually says for commercial building. Now we have also codes for residential buildings as well. So we have different kind of code which sets minimum requirement, how the building should be made energy efficient, what will be the minimum requirement for making a building energy efficient, and the construction of the buildings. And then if you look at this, like what I was telling you about the governance system, we have different governance in place where the central government has a role of developing all these codes. State government has the role to amend the code as to meet the state specific requirement, to notify it in the state gazette, then revise all the development control rules, model building bylaws, etc. And then we have a role of local government which actually help us in enforcing it in the at the grassroots level, like revising the urban local building bylaws and approval process, that the building approval process that we follow, enforcement of ECBC, etc. So now as an architect, once we start developing or upgrading ourselves, we plays a bigger role in the industry. We can also support, once we have all these understanding of the climatology that we study, how to make energy efficient building, how to apply the climatology to develop sustainable building design and all, we can actually help the system, or we can also support government to implement all these things. And we can also support to do the capacity building of all the stakeholders in the industry, the designers in the industries, to help support the implementation of energy efficiency in the system. So as I've shown you the code, energy conservation building code, it has, 4 major components. Envelope, the building envelope, we all know we have to make the code specify the requirement for optimizing of building envelope. What are the specific, what will be the U value of the building assembly, that wall assembly that we are using, the roof assembly that we are using, and the fenestration, what will be the specification of fenestration that we are using in the building envelope. Then the lighting and control system, what are the actual specification of lighting and control systems that we are using to meet the energy efficiency performance of the building, comfort systems and controls that we should be using. And the fourth component is the electrical and renewable system, so that what kind of system should be in place to meet the energy conservation requirement of the building code. And if you see the applicability of it, there are certain mandatory requirements that we need to follow. And then to make the compliance approaches, we have different methods of it. Like there is in the code, if you see, there is a prescriptive method which specifies each and every requirement of the U value, the U value of roof, wall, fenestration, what will be the SHGC coefficient, and all these components. And we need to meet and comply all those requirements to comply with the energy efficiency building code. But and on the other hand, there is a second approach where we have a whole building performance method where you can do the simulations. We can do energy simulation, and we can actually calculate the energy performance index of the building. And we will see whether the EPI that we have received from the simulation is actually complying with the energy efficient energy conservation building code requirement to make the building ECBC compliant. And if you see the overall impact of energy efficiency in the building, so this
I have not.
sorry, hello, is someone saying anything? Okay. So moving ahead, this is just an example that I have taken it from few of the projects that we have done, that how by complying with the ECBC code and with different incremental level of ECBC code. I'm sure you might be knowing this, that for ECBC you have three different incremental level. First is, you need the first level is ECBC compliance, then ECBC plus compliance, and then super ECBC compliance, to make it more, to save more energy by growing more stringent or aggressive in our approaches to implement the energy efficiency measure. And this is how it contributes. Like, it can actually reduce, your energy consumption demand from 25% to 45% of, by reducing it from 25% to 45% of the electricity or energy consumption demand. So these are few of the cases that I wanted to show that I have done in my previous, engagement with different companies. When I was working with ECBC Cell, we have to do some demonstration projects. So I've put together a few examples to show you. This was a girls' hostel at Goa Medical College and Hospital, where we have actually done the analysis and tried to see that how much of, the proposed design can reduce the energy consumption and what will be the EPI ratio. So if you see, we have tried to reduce almost like 45 to 50% of the electricity consumption by doing the energy analysis, and by suggesting various energy efficient interventions in the building. Another example, how the same example, how we have done the sun path analysis for the building, how much of the heat gain that we are getting, how much of the daylight that we are getting, useful daylight that we are getting inside the building. So this is another case study that I have put together from my desk research. It is a IIT Kanpur building, where, if you see so this is like the indicator figure, where the initial energy consumption was approximately 240 kilowatt per meter square year. And by implementing all these energy efficiency measures, by optimizing envelope, it is reducing 13% of the energy consumption. Like, all the measures and interventions are mentioned here. You can just go through it, but I'm trying to give you the summarized version of this whole analysis. Like, by envelope optimization, by making the envelope efficient so that we can reduce the heat ingress inside the building, we have reduced 13% of energy consumption. By lighting optimization, we have further reduced the energy consumption to 19%. So see here, like in green, you can see how the EPI is changing. The lesser the EPI, the better the building is performing. So earlier, if you see, in this, I have mentioned 240 kilowatt per meter square year. So if you see how it is reducing, after building envelope optimization, it has reduced to 208. Lighting optimization, it has reduced to 168, which is almost 19% of energy saving. Then HVAC optimization will reduce further to 26% of energy saving. Yeah, we will not reduce, it will contribute to 26% of energy saving, which is like 133 EPI. And then using controls and all, you can further reduce down the EPI to 98. So you can actually see the different impact of energy efficiency measures that you are applying in the building, and how your building is performing, and how much of energy savings that you can achieve by just applying all these measures. So almost like 60 to 65% as energy saving is indicated in here, if you do all these kind of optimization in the building. And what is the impact of energy efficiency in the market? We have to set a minimum standards, and we need to push the market by doing different R&Ds, incentive rating systems. We are going to pull the market, and then we have to actually establish the market to set, to make it prepare for more energy efficient to incorporate more energy efficiency measures in the industry. Because see, I remember when there was I'm just giving you a simple example, that earlier when we used to buy a LED bulb, it used to cost, it was earlier very costly, but now we are getting it in a very cheaper price. So this is how the market push itself. So if you create the demand, if you actually start making building in that way, the market, you are going to actually pull the market, and you're going to set it for more energy efficient products in the market. So this is where we as an architect or design professionals, it is our responsibility to set up everything to promote energy efficiency in the market. So to summarize it all, building energy efficiency goal is, like for example, there's a conventional case, we have this certain energy consumption in it, we need to put more focus in the embodied energy analysis also for the building materials or the building design that we are doing. Sorry, building design that we're doing, then we need to we need to put together our different approaches, whether we'll be going with 25% of energy saving ECBC plus, then super ACBC, which can contribute to 45 to 50% of energy saving, or you can actually go towards to the net zero approach by further reducing the demand of electricity and offsetting it through renewable sources. And then even you can make efforts with your design decisions and all, you can also make the building net positive. Over the years, net positive buildings can become the carbon neutral. So we need to put our effort in the right way, in the at the right direction, so that we can achieve all these energy efficiency goals. And now we have also, like if you have seen, like we have the national and international commitments that we have done to reduce it, the energy performance, to reduce the energy consumption and going carbon neutral in the near future. So we need to put and make our efforts in the right direction. So the fifth vertical is adding knowledge and capacity building. So here, if you see, we all have knowledge. We know that we have a set of understanding, but we need to actually try to use that knowledge that we have by doing capacity building, by doing more awareness. You have to add more knowledge, market push, etc. So if you see all these workshops that you can do, all these all these topics that you can understand to improve your knowledge in terms of building physics, in terms of energy efficiency in buildings and analysis, energy simulation, daylighting simulation, CFD simulation that you can add on to your knowledge. Then you can also understand what is the amalgamation or of environment impacting features. Then you can also understand how do you actually, calculate the environmental impact assessment, how you can actually do the environmental impact assessment, what are the best practices in architecture and construction, MEP, etc., how to calculate water efficiency. And also there are different workshops, seminars, there are different tools, there are different courses where you can actually enroll yourself to upgrade your knowledge, to actually understand that how these softwares on the left side, what I'm showing, how these softwares are performing, how we are actually improving the, and not forget about improving. Now first we need to understand that how our building is performing, how the wind circulation is happening inside the building, how the heat gain analysis is happening, how the heat gain is happening inside the building. So all these kind of analysis we are supposed to learn, we are supposed to do, so as to upgrade ourselves and become, as I said earlier, the pro version of ourselves. So these are a few glimpse of analysis that I've done in my previous project, that this is how the design process decision that we used to take based on the climate analysis. So this was the climate analysis for Kano, the African, that's an African city, how the heat map will be, what will be the wind direction, from where the prevailing winds are coming, what will be the solar path of it, so as to understand how many sun hours that we are getting inside the building. So these kind of decision making you can do while learning all these process and understanding the climate condition of the building. Sorry. Then we have developed different kind of, you can develop different kind of design support matrix, that what will be good for the macro level, macro scale, what will be good for micro scale, what will be the good strategy for meso scale. Until and unless you will do all these kind of design decision making, your design is not going to improve. So we need to put together everything, all our understanding, to make the right right and specific, to select the right and specific intervention for any building design, or let's say at the urban level design. So what will be the impact of climate at the building, and what will be the impact of orientation of the building, what will be the impact of sun direction of the building. So we need to do all these analysis at the design stage itself, when you're designing something. By just after your architectural designs are freezed, you can start doing all these decision matrix by your own, if you apply your climatology knowledge in your building design. So if you see, we have done this shading analysis, shading time analysis of the campus, that sorry, what will be the impact of how the shading will be during the, so you might have seen, I have mentioned here the summer solstice and the equinox. So can anyone tell me what is summer solstice and what is an equinox? trying to see it's in the chat. Nobody is answering. Yeah, this. Can anyone tell me what is summer solstice? We all know climatology. Hello, is there anyone listening to me? Okay, so I'm going to ask this question in the quiz and let's see who can answer this question. So I'm going to move ahead. So these kind of analysis that we used to do for shading time analysis, because because it is considered to be the peak day or the critical day for any design, and to achieve and we to maintain the discomfort hours and to understand the discomfort hours inside the building, we need to understand the critical and the peak period. So that is why it is required to understand what is, when there's a summer solstice, what happens, when there's an equinox, what happens, and how to design a building in that way. And I'm going to ask this question. Nishta, just make sure people answer these questions. Okay, so moving ahead, then we have also done we have also done this mutual shading analysis for our design, which you can also perform once you will understand that, even just by placing the building clusters, how to place the buildings together so that they should have an impact of mutual shading. So if you just see, this was a simple understanding that if there's a building without shaded, and then if there is a building with mutually shaded environment, then it can actually contribute to 35% reduction in the solar radiation exposure, and it will actually contribute to the EPI reduction. So we need to understand how to quantify the impact of mutual shading, how actually the shading is impacting the design and making, and what will be the impact of shading inside the building, so that we can understand how to orient our building, how to locate or place our building at the site. So this is all important to understand how are we going to do the different kind of analysis. Then for natural ventilation, we all know that, how we have to put a lot of window, but we need to also understand the principle behind it, how the cool air will come, how the warm air will exhaust out. So we need to design our windows in such a way so that we can actually understand the whole mechanism of the airflow inside the building, and how to, exhaust the warm air that is trapped inside the building. So what will be the process and how to apply it, that needs to be understood for a natural ventilation process. So these are few of the case studies that I've put together. This is for IRR 80 building in Gurgaon. So just see how, I mean, a simple intervention can provide a lot of thermal comfort inside the building. By look at the shading devices and how the impact of shaded envelope can create in the building. This is another, so this is the another glimpse of yeah. So this is the glimpse of how the services are designed. So if you see, all the ducts and services are integrated inside the structural system, so it is not visible from outside. So that is where, if you do a design, share it at the initial stage itself, aligning all the stakeholders related to the building design together, the architects, the MEP consultants, the HVAC consultants, then the green building consultants together. This is how your design will evolve, that you can minimize the construct you, like as I've earlier mentioned, that you should actually understand the unnecessary use of components, the superfluous nature of it. So you need to understand how to optimize the construction, how to use the less resources, how to put the less material, and how to use the less material to actually make a structural design look beautiful without adding any additional feature and additional cost to it. So if you see how the ventilation system and the false ceilings are minimized by installing to house the HVAC and the fresh air ducts inside it, and there is no additional components inside it, which is in turn resulting into the reduction in the usage of more materials and structural requirement of it. See how, so this particular building, why I'm trying to show all these examples is, we are not we are not trying to do some rocket science here. It is our simple understanding, and our design process has to be in such a way so that we can use our design in terms of making it more efficient, more responsive towards the climate. See, there are no windows, sorry, there are no dependency of artificial lighting in here. So there are very few lights here, but see how beautifully the skylights are designed to allow the daylight inside the building, and how naturally lit this particular space is. And until unless you will take this decision at the design stage itself, you're not going to get such beautiful designs. So this is where the climate responsive design is important. If you see how building envelope, massing and passive system proposals that we have made, we have tried to understand how the building and building orientation, the site orientation should be during summer, how will it perform in winter. So these kind of analysis that we do to understand, what will be the integrated approach for making, getting the grip of fundamentals of building physics, that how the massing should be, how the heat gain should be. So we need to understand what are, how the building physics will work, and how we can use the actual, attributes of building physics in the design, in designing the building. So this is the impact of natural mechanical ventilation, where, where we have actually seen the strategies versus the with the windrows diagram, that how it is performing. So you can, and you can develop, you can orient the whole, components or the clusters in your site to get the more advantage of, prevailing wind. So how from which direction the prevailing wind is coming, how you can actually invite that wind inside the site, so that, all the buildings get naturally ventilated. So if you see how what is the impact of building envelope, if you see here, this is the building business as usual case, which is basically the base case, what we say. Then there's an intermediate case, and then there's the efficient case. So what kind of materials that we use to reduce the, heat ingress inside the building, for wall, for glazing, for roof, for floor, for shading, for solar PV roof. So you can actually try to achieve the, you can actually try to reduce the EPI of the building. So this is how, if you see here is the indicator, the legend that shows that how the building performance is improving with efficient cases. Then if you see building envelope for the daylighting analysis, then so how you should, how to design your WWR, what will be the size of the windows, at which direction you are orienting it, and at what is the impact happening at different floor levels. So we can do all these kind of analysis if we know the right software and we have the right understanding for it. So we need to upgrade ourselves to understand different kinds of impact. You can simply, just by doing all these kind of analysis, you can actually quantify it, that how much of daylighting that I'm getting at first floor level, or at third floor level, or at eighth floor level. So we can understand all these kind of, we can do all these kind of assessments. Then artificial lighting control. Just run this. Okay, so this video is not running, but yeah, started. So what will be the impact of artificial lighting, how to design the controls and all. This is all we can do with different softwares. So which I'll be listing down in the end of the presentation, that how the daylighting sensors will be can be installed, how it will assess motion, what will and the infrared sensors can be installed to understand the motion, and where if you have the, if you have someone sitting, then the lights will be on. If you're not using, if you're not there, then there will be no light. So all these kind of analysis and assessment we can do at the design stage to understand how our building will be performing, so that we can not superfluously using the artificial lighting, and it can also help us in reducing the dependence to use the mechanical system. So this is how, and then I just want to show a glimpse of the project that we have done. It was one of the resort in Hamsa Valley, and then we have done different windrows analysis for wind direction to understand the wind profile of the site and how to design the building in such a way. And then we have done the solar radiation, the sun path analysis to understand the sunlight hours, how much of sunlight we are getting, how much of heat gain will happen in each of the building, what will be the impact of mutual shading and all. So we have all done these kind of analysis, and then we have come up with the design that this particular design will be best and will have the optimization of resources. It will be energy efficient in nature. It will be thermally comfortable in nature by doing all these design analysis. Then there was
This is
another
again a
project.
project with Matra Architects for Sant Niwas, New Delhi. Considering the extreme
I think there was some sound also in the background. So there was another project that we have done for different kind of strategies that we have, used in. So there was this project called Sant Nivas, where we have to look into different strategies and for the walls, because they don't need any disturbances, because of the fan, because of the cooler, or because of the air condition, because they need to meditate. So these were three different walls where we have identified different strategies for the wall, like radiant heating and cooling, phase change materials, thermal massing, and all. And for different for different walls, we have analyzed how the radiant cooling will perform, from where, at which side we need to apply, at the wall, back side of the wall, or at the roof side of the wall. So different locations we have analyzed. And then for the second wall, there was the phase change materials. So phase change materials are the salts. So we have actually applied the phase change materials from the roof, or on the floor, then on the wall, and then on the roof. And then there will be a air inlet to recharge these phase change materials, so that once they are charged, they can actually dissipate. They can actually dissipate the cool inside the vault, and then it will make the vault thermally comfortable. And and then I don't know, I mean, if you have heard of this material, these are actually like revolutionary materials that are there in the market. So it is all understanding of the materials, what are available now these days, what are the trending markets, to then it will be you will be able to understand that what will be the impact of these materials when you apply it in the design. Then in the third wall, we have tried to analyze the thermal massing performance by actually introducing the thermal mass with low emissive paint, and then how will it perform. So all three walls, we have tried to analyze different type of strategies to make it thermally comfortable without having any disturbances, because we need to have a right amount of thermal comfort inside these walls, not so cold, not very hot. And then we have, and these strategies were the this is these are the strategies that we have explored for the proposed walls. So different kind of radiant cooling, space allocation, modular chillers, and all. So where to locate it, how to design it. The floors were with radiant piping routing at basement floor to and the upper floor. So these were the designs that we have proposed, the interventions that we have proposed to make the building more thermally comfortable, and also with keeping in mind that it is energy efficient also as well in nature. So in the end, I just would like to tell you that it is not just practice. So we all need to practice design, not decoration. So our sole responsibility is, we need to put each and every element, we need to design each and every element so consciously that we should understand that we are not overdoing it. And we also have to understand that we are not designing any building for just for the sake of designing. As I've mentioned earlier, it has to have some purpose. So this is what is the tip of the whole session. And now I think the this particular session is over, but I would just like to have an interactive round just to understand the principle of it, and to have an interaction for understanding the concepts and fun facts of the climate responsive architecture. So can I ask some questions? And not the questions, can I ask any of you to just answer that, what exactly is this and how does it perform? What is this strategy that I am flashing on my screen? Can anyone tell me what is the system?
Participants, if you want, you all can unmute yourself and speak, or if you're not comfortable in speaking, you can also write your answers in the chat.
So it's a very simple question. It's a very simple technology to start with. Anyone can unmute and answer. What is this? What is this technology that I'm flashing here? Is this a glass window? Okay, I mean, maybe you can, yeah, solar panels on the south wall. No, it is not a solar panel. Anyone else? It's a very famous technology. It's a very, not technology, I can say it's a very famous system. That the first thing that we learn when we, try to understand the various passive design strategies in the cool climate. Perfect, Nitin. Trom wall glass or solarium? Yes, it is a trom wall glass. Can you unmute yourself, Nitin, and can you tell me how does it work?
Good afternoon, ma'am.
Yeah, hi, good
Actually,
afternoon.
things like in colder countries, like we need to get high radiations, so long wave radiations basically to heat the environment. So this will be there will be another wall or something behind this glass wall, usually for trombe or glass solarium, and that object will be get heated up, and then afterwards in during night it will be re-radiating the heat.
Yes, yeah, this is so basically there is, this is the glass wall with and there is a wall behind it, and then the wall surface is of dark color so that you can actually once the solar radiation falls into it, and then there's a air gap between the two layers, and then so the air gets heated up and warm heated air goes inside the building, and then the trapped air circulates, the cool air circulates out, and then it goes through this air cavity. And then the conventional cycle of air happens, and then the air rotates and try to, and there if you see here my if you see my cursor here, uh, there are different holes. I don't know, is anybody able to see the cursor that I'm flashing? I don't think it's visible. So basically, if you see the bottom of the glass behind, bottom of the wall behind the glass, there are different openings, the small openings, which is actually allowing the air to circulate. The cool air is coming out from inside, and then it is getting warm, and then from the the voids that is designed on the upper side of the wall, and then this is how the air is getting circulated. The warm air is getting inside. Yes. So thank you, Nitin. Then the next question is, what is this? What is this? Like, what is this solar design, passive design feature? So I think Nitin has already answered this. So earlier was prom wall. This is a sunroom, also known as solarium, where you can there is a glass wall, and then there's a buffer zone and there's a deck where the you can actually it gets heated up during winters when you get the sun, and then the buffer zone traps the heat, and then it circulates inside the other livable areas. So this is the sunroom. This is also another example of sunroom. Now, what is this? So this is a combination of trom wall plus sunroom. So you have a darker wall also, and then you have a window opening also, so that you can actually trap the heat here during, so that you can actually utilize the maximum sun gain from here, and then you can recirculate it inside the livable, like all the livable rooms that you have. Now, can anyone tell me what is this construction technology, and what is this particular building typology? What is the name of this particular building typology? If you are not gonna answer, I'm gonna ask. I'm gonna name the participants to answer this. Barka Soni, if you can just answer, what is the typology of this housing or this building? Come on, it's a very simple question. I am sure many of you have seen this house. Many of you have visited this place. It's in. Let me give you a hint. It's these kind of houses or buildings. We make it in cold climate of colder climates here in India. No one. Kart Kuni architecture. Perfect. Yes, it's a Katkuni housing. So you have, wooden planks in between the structural system with stone, and this will help to insulate the building envelope and reduce the heat, the trapped heat inside the building outside, so that the indoor environments remains thermally comfortable. Perfect. Thank you, Nishita. Nice. Thank you, Nishta. Okay, Nishta, you are answering the questions. Okay. Coming to the next slide. So, what is this? These are Naluketu house in we usually see in Kerala housing. So they have a typical architecture with big overhangs and steep roofs, and then you have a central courtyard to have, so that the fresh air or the cool air should come in, and then the hot air get exhausted outside. So this is a typical housing technology, housing typology that we see in Kerala housing, because it's a warm and humid climate. So we need to make sure that they have a typical humidity condition and a typical heating condition. So we have to design the houses in such a way so that there has to be a proper ventilation. There is no trapping of heat inside the building, and there is a proper circulation of air. So for warm and humid climate, it is very important to understand how the ventilation is. Only with very good cross ventilation strategies, we are able to make a thermally comfortable environment. So this is how it is. So this is how the Nalketu houses are designed in Kerala. This is another example of Malay house. Again, the design strategies have, if you can see the schematics here on the right hand side, and then you try to relate it with the house that picture that I've shown on the left hand side, how nicely they have designed spaces to make maximum use of wind, and so that there will be a good cross ventilation and there is no trapping of heat inside, and then to make the buildings inside thermally comfortable, they have designed the houses in such a way, the windows in such a way, so that you can utilize the wind, the prevailing wind direction of that particular area, to get so that there is no heat trap inside, or there should not be increase in humidity inside the building. What are these? Anyone can tell me? I'm sure someone might have done their, I mean, there are 37 participants. किसी ने तो इसमें research किया ही होगा. Because this is a very many people, they try to understand the technology and how the design architecture of these particular buildings are, and they do a lot of research in these kind of houses. So these are pole houses. You can see it in Gujarat. So these are pole houses. They have less exposed, very shorter areas exposed towards the sun. They have a small courtyard or kind of a chalk in between the houses, so that you can have a proper cross ventilation, and with stack effect, you can actually exhaust the trapped air coming out of the livable spaces. And then, because all the houses, if you see, they are so tightly designed that very shorter facade is exposed towards the direct sun exposure, so that you can reduce the heat gains. And then all the windows are provided with the shading and chajja. Now, okay, the name is flashing itself. So this is Kachi Bhunga. So these are the housing typologies Bhunga, which you see in the Kutch regions. So they have this typical style with very steep pitched roof structure with all these white paints and mirror works outside. If you have ever been to Kutch, you might have seen that they have designed very nice murals on the wall with placing all the mirror work and all. And the idea behind it is because the idea behind doing all those murals and all, to make a self-shaded facade, because all these mural designs, when you have some extruded surface on the envelope, it will have all these shading impact. They provide a little and short shadows on the envelope, then you are putting all these white paints and mirrors. So now just imagine, these people are doing this in such a long time by reducing by putting all these reflective making all these reflective surfaces. The mirror and the white surface actually help to reflect all the sunlight that is falling on the envelope. So with all these circular form, with all these white paints and then mirror works and then mural design and all, they are actually trying to add more shading to the envelope. They are trying to be more they are trying the facades to be more heat reflective in nature. So there, these surfaces are tried to make with more reflective paints, like the white paints and all. The mirror work is actually reflecting back the sun radiation, so that the heat gain is less inside the building. So this is how design principles they follow for making the Bunga design. Now, this is a very good structure. Has any one of you ever wondered that if you're living in such region, why are you living in, if you have so many snow surrounding you, why are you making a building out of snow and then you are living inside it? Can anyone tell me what is principle of designing the igloo and how does it perform? Anyone knows? I mean, just unmute and you can also unmute and answer, because if you're not, if any one of you knows about the principle of designing an igloo and how does it perform, so maybe just unmute yourself and answer it. It has a very simple principle. So where the blocks are made up of snow, and the snow has a very it has a very low thermal conductivity. So what happens is, when you make the building out of snow, then it provides you insulation as well, and then you actually dug a little bit of the snow from to enter inside the igloo. And then once you are inside, your body temperature, and if you're lighting something, let's say a little candle, or if you're providing a little light, and with your body heat, what happens is the first layer inside the igloo melts, but melts and then it freezes, because the outer temperature is cooler, and then there is a slight melt the first layer of inside the igloo. And then once it melts and freezes, it actually insulates the entire surface. It actually packs the entire surface, so that there is no heat gain inside it. So it becomes like a complete buffer zone, and there's a small vent on top of the igloo, so that if you are if you have if you have lit a candle, or if there's a small fire that you have lit to make the indoors little bit comfortable, so there is no smoke trap, so there is a vent. So because of that, because of the body heat, and because of the small light or candle that we have lit, it becomes warm inside. And because of the the thermal conductivity value of the snow, there is very less heat in the temperature. There is a very it has a very good insulation property. So then that makes the environment, the indoor environment, more comfortable. And with this vent, there is no trapping of the smoke or if anything. So this actually helps you to exhaust the trap air or the stale air outside. So this is how igloo works. Then there is another example of this East Gate building. So this building, I'm sure you might have also you might have studied the case study of this particular building. So this is basically designed from taking the reference from the ant hill. So what they have done is, so they have designed in a way so that there is a central system, and they have blocked, like they have created all the buffer zones from outside, so there is less heat direct heat ingress from outside. What they have done is, they have created all these mechanical systems, so that all the warm air trapped from the rooms from both the sides, it gets exhaust from the central spine line that I have shown in the right side of the picture. So it gets exhaust from the spine line, and then there's a mechanical system to exhaust the warm air, and then you cool the building. So with such kind of design principles and all, they use very less, so the energy consumption, they have reduced the energy consumption of the building over the conventional building sizes. And then if you see in 5 years, like the building is performing, and it's more efficient in nature, and it's more thermally comfortable in nature. And again, it is inspired by what the nature has designed for us. So these are few of the buildings that you can actually try and study to understand how how to mitigate the challenges that we are facing of making, which are making building thermally uncomfortable, and what can you do, and what can your strategies would be to actually make the buildings more comfortable. So if you see, this is a very nice structure that always catches my eye, because I tried to study this particular structure a lot. This is actually a bamboo tower which creates 25 gallons of drinking water per day from the thin air. So what they do is, if you see from the left hand side, this is actually a spider web. If you see with this principle, what happens is, spider web, they actually it traps the moisture from the environment, and then you might have seen these kind of droplets get accumulated on the spider web. The similar kind of principle they have applied in this particular tower. So they have a very fine mesh, and they have created this tower, and because of the the air moisture present, and the air the water droplets present in the air, it gets trapped here in the mesh, and then they collect it below in a bowl. And with this, they're trying to mitigate the water scarcity at that particular area. So these are called Varka water towers, which you can try and read more about these kind of strategies to understand how to use and reuse the resources that are available at site. So with this, I'm going to end the session. For a responsive design, we need to have some empathy towards the culture and the climate. We need to also integrate it with the aesthetics. We have to have a proper integration of climate requirements for designing a building. And then comes the technological advancements, and we need to integrate we need to integrate our understanding. We need to upgrade our understanding to understand the technology. And with all these four parameters, we are going to develop an intelligent design, resulting into the commitment of excellence, integrated planning, and the focused effort. And with this, we'll be able to design a climate responsive building. So I'm going to end this session here, so that maybe we can take a quick break, Nishta, and or how are you planning for the next session?
Yes, ma'am, sure. We can take a break. Ma'am, how much time will you be needing? If you can just tell me, I'll ask the participants to join back at that time.
40 minutes, like we can go with the usual break time that we have, because in the second session I would just like to tell more about what are the simulation softwares, and how in different type of softwares available and all.
Meet back at 3 o'clock then. From 3 to 4, we get 1 hour.
Yes, yeah, no problem. 3 o'clock is fine.
Okay. Thank you so much, ma'am. The first session was really enriching. Of course, it was a very good brush up to everything that we have already studied, but a new take on some of the things that we know very well as well. So it was very great. I am even more excited for the coming session. So I think it's time that we also give some break and some rest to you. Um, Ma'am, let's meet again at 3 o'clock. I
Yeah.
request all participants to please join back by 2:55.
Okay.
Okay, thank you. Everyone, please be back on time. Welcome back, ma'am. I welcome each and every one of you again in this second session of the fourth day of Faculty Development Program by Amity University, Chhattisgarh. Before we broke for lunch, we were learning about climate responsive studio design. We learned about many aspects of climatology, of climate responsive architecture, and ma'am also gave us many examples, specific case examples of different types of vernacular architecture, climate responsive architecture techniques, and how we can also apply some of these theoretical aspects that we have studied in our design studios. At the end, ma'am also took a quiz sort of a thing where she was showing us some pictures and asking few questions. And I really appreciate your active participation. It is such a joyous thing for us when we are organizing something like this, and all of you are actually enjoying it, gaining something from the lectures that we have organized, and you're also actively participating in the conversations that are happening, in the interactions that are happening, because that shows us that our efforts didn't um they were just not like that, but they actually mean something to so many people. A lot of people might have gained something from it, or at least a new perspective was shown to you through this faculty development program. So I would like to thank all of you, because you are also investing so much time in this, and your active participation is something that boosts us and motivates us to do more of these events in the future. We will reconvene with the discussion on climate responsive studio design, and here we are starting with the second session for the day. Ma'am, you can take over.
Yeah, thank you, Nishta. So, hello everyone. I think you have all had your lunch, and yeah, as Nishta has mentioned that earlier I've taken the quiz. No, it was just interaction between you all so that you don't sleep. But I have a surprise for you before we start session 2. And the surprise is, let me know if you can see the full screen. Is it visible?
Yes, ma'am, it's visible.
Okay. So the surprise is a surprise test, and so I want at least try. I mean, just try. I would request all the participants to just try, because we have already done the session 1, and I just want to understand, like, if it is not about you have listened it or not, and if you have heard the session 1 or not. It is just about to test your understanding, whether you know the answers or not, and it is not about right or wrong. So I would just request everyone to at least try and let me know. They're like very simple questions, and I would like whoever knows the answer, just unmute yourself and let me know the answer. Okay, shall we start? Just quickly write in the chat yes or no, and you will get 10 seconds to answer the questions. They are multiple choice questions, so it will be very easy for you to answer it, and you will just get 10 seconds to answer the question. So let's see how. Let's play a fastest finger first here, and let's see who gives the right answer. Shall we start? Yes. Okay, great. So the first question is, which of the following greenhouse gas is the major stakeholder with highest degradation time horizon and warming impact? These are your options. Let me know which is the gas which is the major stakeholder for the highest degradation time, with the highest degradation time horizon and warming impact. It is option 1, 2, 3, or 4. Great. Perfect. Okay. Moving ahead. So guys, it's CO2, carbon dioxide. You are all right. So whoever has answered the question, thank you so much. We're moving ahead with the next question. So the next question is, what is a greenhouse effect? It's the name of climate change legislation that passed by Congress. Option 1. 2, when you paint your house green to become an environmentalist. Option 3, when the gases in our atmosphere trap heat and block it from escaping our planet. Or option 4, when you build a greenhouse. Option 3. Perfect. Good. So yes, the correct answer is option 3, when the gases in our atmosphere gets trapped, it traps heat and block it from escaping our planet. Now moving ahead, which of the following are the consequences associated with the climate change? Option 1, 2, 3, and 4, or you think that it is all of the above? First, the ice sheets are declining, glaciers are in the retreat globally, and our oceans are more acidic than ever. Or it's option 2, surface temperatures are setting new heat records about each year, or we are facing more extreme weather, or there is a global sea level rise, Or you think it is all of the above? Yes, it's all the above options, like all the above statements are correct. That is why we actually need to focus more on addressing the issues related to climate change. Moving ahead, what was agreed in the Paris Agreement that came out of COP21 held in Paris in 2015? I think I've mentioned this term. So let's see who can answer this. Option 1, to protect biodiversity and end of deforestation of the world's rainforest. Option 2, to keep global temperature rise well below 2 degrees pre-industrial levels, or to pursue a patch to limit warming to 1.5 degrees. Option 3, to limit sea level rise to 3 feet above current levels, or option 4, to pursue a goal of 100% clean renewable energy. Yes, I can only see 3 people have answered the question. Yes, yes, Babita, Gayatri, and Kritika. Yes, it's option 2, to keep global temperature rise well below 2 degrees centigrade with pre-industrial industrial levels, and to pursue a path to limit warming to 1.5 degrees Celsius. So yes, it is option 2. Okay, great. I want others also to answer. I mean, there are very few people who are answering, and don't just answer the easy question. At least try. Well, either it will be right or wrong, but at least it will give you some understanding. So I would request everyone to just answer the questions and at least try and answering the question. So moving ahead with question number 5, the Energy Conservation Act has been enacted to encourage efficient use of energy and its conservation. Is it true or false? True, yes, yes. Great. It was a very simple question. Okay, then moving ahead. So this is a tricky question. I want to understand your understanding. So under which amendment India committed to lower consumption and production of hydrofluorocarbons, HFC, with high global warming potential, GWP, by 85% before 2047? Is it under Kigali Amendment, under Montreal Protocol, or it's under Energy Conservation Act, or it's Sustainable Development Goals, or you think it's option 4, all of the above? Yes. Yes, right. It's option 1, Kigali Amendment under Montreal Protocol. Great, Gayatri, great. I think 2 people have answered this, 3 people, 4 people have answered this question. Very good. Okay, moving ahead. Energy Conservation Building Code is launched under which act? National Electricity Policy, Sustainable Development Goals, Renewable Energy Certificates, or Energy Conservation Act? Yes, perfect. Yes, it's option 4. It's launched under Energy Conservation Act. Then the next question is, what is the timing to introduce design share for an integrative design process? Concept and schematic design stage, design development stage, construction stage, or none of the above? Yes, this is right. This is, I want others also to answer. Yes, it's concept and schematic design stage. Correct. So this is the last question. 1 kilowatt hour results into how many grams of CO2 emission? 750 grams, 200 grams, 820 grams, or 500 grams? I promise iske baad aur koi question nahi hai. So this is the last question. Yes, it's option 3. I think someone has answered option 2 also. No, this is the correct answer is 820 grams. So with this, we end the quiz. And thank you so much, everyone, for participating. And I'm happy that most of you have got the answers right. They were very easy questions. And thank you, everyone, for at least trying it. So moving ahead. So the next session is on understanding the thermal comfort and energy efficient material strategies. So I have taken composite climate here because I understand like most of you have maybe are joined from different zone of from in India, but I have taken the composite climate to give this to give the examples of all the thermal comfort and energy efficient material strategies. So, computer stuff. 1 second. Yeah. So what is a building envelope? As I've discussed earlier, building envelope comprises of foundation, exterior walls, roofing, windows, and doors. And as we have discussed earlier also, the heat gain through through building envelope happens through conduction, convection, and radiation. And the major uh, role of building envelope is to give us a protective environment. It separates the indoor environment from outdoor environment, and it also helps in giving us a thermally comfortable spaces inside the building. So what is the approach for high performance building envelope? So a building envelope has to be sustainable in nature. Its safety is very much important. Its historic preservation attribute is very important. Its functional aspect is very important. Its cost effectiveness is very important, and its aesthetic is also very important. So if a building envelope has all these 6 features together, then we can say that yes, this is the right building envelope that we have designed, or it is the right approach of designing a high perform a building envelope. So what is the road towards energy efficient building envelope design? So if you see the old stock as in not the traditional or vernacular architecture I'm talking about, the old stock as in where we have just without giving a thought of how to design a building, when we have designed an inefficient stock of building envelope. So these are like, if I just quote few examples, with single pane windows, they have air leakages, they have no insulation, which actually contributes to more heat ingress inside the building. So with typical building code, like if you have to set a building minimum requirement of building, achieve the building code, and to at least achieve the minimum specification of building envelope requirement, you will be applying, let's say, low E double glazed windows, or with low air leakages, or with high insulation. But for a higher efficiency, you need to be more stringent, or you have to be more aggressive in your building envelope design, where you can actually use highly insulated window, optimized design and orientation with good material composition and all. So this has to be the approach. If you have to, so basically what you need to do is, the process is to understand the where are we going inefficient. You need to analyze the old stock of the building, how and in which parameters they are insufficient or inefficient. And then you need to understand that what will be the minimum requirement of the building code, and how can you make it more efficient, right? So this is how the roadmap will be like. Define the purpose of the need, then identify the scale and interdependency. You need to also identify the functionality of the envelope. Then you identify the possible problems associated with it, that if you have if the conductivity is very high, if you have lot of air leakages, if there is a high level of heat ingress inside the building. So you need to identify all the problems associated with it. Then you identify the technological solutions for it, and then compare all the solutions with financial implications. And then you have to provide the best outcome, which will be efficient and cost effective in nature. It is nowhere mentioned that we have to incorporate or implement very high end technologies and increasing the cost of it. If the best ideal way to propose a building envelope design is, it has to be efficient, energy efficient in nature, and it also has to be a cost effective, or it will not have a very high cost associated with it. So this is the roadmap. So for a building envelope analysis procedure, we have different stages like programming, conceptual designing, design development, schematic, and final output. And how you do it is, you can do daylight and insulation study. Sorry for the spelling mistake. Daylight and insulation study. Then you can actually try and understand the building orientation. Then you can understand the facade insulation analysis, shadow analysis, etc. Then daylight study you can conduct for the building envelope. Then you propose the facade design options. Then you can do a daylight study for a facade option. Then for that particular facade, you can do a thermal analysis and then finalize the facade design. And once the design is finalized, you have the building envelope optimization study in your hand, and then based on that you can finalize the building envelope design and materials. So it is very important that you get all the process right. It has to be in a way where you understand that from where you need to start and from where you at where you need to end the process. So for an energy efficiency through building envelope, you can use different simulation techniques to optimize the orientation, envelope, and building massing. You with high R value insulation in the walls and roof that you can implement low U value materials for walls and roof components. You can incorporate insulated glass units with low SHGC values. You can have optimal fenestration and window wall ratio for a building envelope design. You can have vertical facade, green facades or external walls to create, the green roofs or vertical green facades for the vertical gardens in the building. Then you can also propose green roof also upholds the integrity of the building envelope. So you can make all these, you can use all these principles or ideologies to develop a highly efficient building envelope. And if you have to select the materials for this, as we have discussed earlier, there are phase change materials, there are insulated concrete foam for using as insulation. Then you have metal insulated panels. Then you have different building material envelopes, which we'll be talking in these in the slides ahead. And with different material choices and all, you can mix and match and make the combination of a best wall assembly or roof assembly possible, which will allow a very less heat ingress inside the building. So if I have to just look into the overview of, what are the strategies that we need to follow. So first thing is optimization of building shape and envelope with efficient solar design, external movable blinds to control heat gains, compact building shape for reduced heating demand. You need to optimize building envelope in a way where you actually understand that how the building blocks are getting shaded, if there are any thermal bridges, if the construction is airtight or not, the building envelope is properly insulated and all. So these are the strategies that you can implement at the building envelope level. Then minimization of embodied energy. So earlier in one slide, I've showed that if you can put, and you can put your understanding for the embodied energy calculation as well, it will help in improving the efficiency of the building. So when I say embodied energy of the building, so it will embodied energy minimization. So it means embodied energy of the building materials of an energy efficient building. And it can be of same scale as the energy of the building operation. So it has to be an equal balance between the operation of the building and the embodied energy of the building materials. Embodied energy of the buildings can be reduced by reduction of mass. You can have a compact shape building design. You can have efficient load bearing structure, not necessarily, no unnecessary material layers. So it is all dependent. It's not like this is like a generic solution for everything, but you have to have a mix and match of the understanding. You have to understand the site specific requirement, and then you can suggest the materials. You can suggest the materials resistant, high resistant materials with long lifetime, regional available materials with low embodied energies and all. These are all you can actually do to minimize the embodied energy. Then once you have done the envelope optimization, you have given the thought for embodied energy minimization, then you can look for the efficient mechanical systems. So we know that we have, our thermal comfort level has changed a lot, and it is a very generalized term. My thermal comfort level, my comfortable level will be a different, at a different temperature. Maybe your comfort level will be at a different temperature. So we need to understand that what is the adaptive thermal comfort level of a human body. So with that understanding, we need to design the building, building facades with all the strategies and all, and then we should also propose a mechanical system as per that. So then if you have efficient mechanical systems, you can have components of efficient building mechanical system by providing efficient heating system or cooling system. You can have efficient ventilation system with heat recovery. You can have efficient equipment and appliances. Keep system and its components simple and easy to maintain. So if if you have a system with an inappropriate building design, then your system maintenance becomes very high. So the building design has to be in according to, the building design and the mechanical system has to correlate with itself. It's not like you design a whole glass building and then you are saying that, okay, I have a very efficient HVAC system, which is going to make the building more energy efficient. No, that's not the case. So we have to have a proper balance of everything. Then coming, then the last part is to actually offset. Once you have reduced your energy demand with all these parameters and all, then you use the renewable energy sources of the building by solar, thermal, solar power, photovoltaics and all, earth air tunnel, and all these clean energy sources which you can integrate in your building to to offset the remaining demand, or at least to further reduce the energy demand. Then you can also look for a net energy, zero net energy or energy plus buildings, can which you can realize it using through the local energy, so renewable energy sources. So that's how the entire canvas of achieving the building energy efficiency or a high performance building design is. So as we have discussed, building orientation can play a major role. So these are the different strategies. So these are some of the case studies which we all know, but we need to apply it in the in the building. So for example, we all know that building orientation is very important. Orienting the building in terms of with respect to the prevailing wind direction, composition of the building blocks in such a way so that we can invite more wind, creating the pressure differences so that we can invite the wind inside and all, and how these how these textbook knowledge will get translated into the actual site is. So here I have tried to show this, that if there is a building cluster, so how the sun path analysis would be, how the buildings will be shaded, what will be the impact of mutual shading, how many hours of sun each and every building will be getting, how to orient the building in the prevailing wind direction. So these kind of analysis you can do from what you have learned from your understanding of building orientation and blocking and marking. Suppose again, building orientation, this is how, like how to design the trees, or taller trees or shorter trees to block the cool air or to invite the daylighting. Then you can also design it where the how to orient your building to get the maximum sun angles, so that you can integrate your solar panels inside the building, how the cross ventilation would be, how the wind circulation will be. So you need to understand and design a building in that way. Then you can also do a condensation analysis. Many a times you might have seen that there is a problem where there is a condensation issues in the building, which leads into mold formation, decay on walls and all. So we can also do the condensation analysis, as we have shown here. We can do interstitial condensation analysis, condensation interfaces, surface condensation, and this analysis and report will give you where actually the water, the moisture is getting trapped, and what are the critical areas which needs to be designed or redesigned to avoid these kind of condensation issues. So moving ahead, like coming to the wall materials, which for which like this session I have tried to put together a few things where I can tell you more about the materials and the strategies. So if you talk about the wall, I have wall is like masonry. The wall assembly can be of comprised of masonry, insulated panels, solar passive facade, or phase change materials. So I've put together a few things, the glimpse of the materials available, so that you can understand how to brainstorm around picking up the right material for the wall assembly. So if you see masonry, just quoting few example, like you can use AAC blocks, thermally insulated bricks, you can use hollow blocks and all, and you can use cavity walls and all. Then if you see insulated panels and all, you can you can actually add insulation to the wall assembly. You can actually add, if there is a cavity wall, that also acts as a insulation and then as a creating a buffer. Then you can also use solar passive facades with green, with integration of movable fins, movable blinds, operable windows and fins. Then phase change material, as I've already shown one of the example where we have used, like phase change materials is the new material that is there in market. Then you have transpire solar correctors, how to integrate these technologies in the wall so that you can actually provide the different kind levels of thermal comfort inside the building. Then for the opaque construction wall, this I'm trying to relate it with the ECBC code. So if you see, like we have different strategies for opaque wall, shading wall, double brick wall, cavity wall, insulated wall, curtain wall. So to understand how, so to understand what is the, so basically this is the screenshot from the ECBC code for composite climate. So it specifies that what should be the U factor for overall assembly, what should be the R value of insulation material, insulation alone, then what is the overall U factor of the U factor of the overall assembly, and the R value of the insulation alone. So we need to try and analyze all the aspects independently. We need to try and analyze the specification of each and every layer of materials used in the wall assembly, and then we need to find out whether it is compliant, because these codes have been developed analyzing different typologies of the building, running multiple and thousands and lakhs of dynamic simulations, and then they have derived these kind of values. So, and these values have been derived for different climatic zones. As I'm sure you might be aware that how Bureau of Energy Efficiency has classified 5 different climatic zones. So these values are categorized for different type of typologies of building under different climatic zones. So what we need to do is we need to do some simple calculations, or we need to do some simple simulation to understand whether we are complying with these kind of values or not. So if I have just shown a simple calculation here. So for example, like let's just see what are the recommended techniques for the wall. Like increasing wall thickness can be one strategy, providing air cavity between walls and hollow masonry blocks, applying insulation on the external surface, using fly ash bricks or AAC blocks, or whichever has the good thermal conductivity value, applying light color distemper or on the exposed surface of the wall to make the to increase the solar reflectance of the surface, applying solar PV on the exterior wall of the surface, so that there is, there is no direct heat gain on the wall, and there, all the heat gain is getting trapped and converted into the in the getting falling on the solar PV and getting converted into the electricity generation. Provided hanging gardens on the east-west side of the building is beneficial in the composite climate, so that there you are creating a buffer zone. So if you see this table below, there's a simple calculation. This is how we do, like this is how you can all do to try and comply the wall assembly or roof assembly with the ECPC code. If you see on the left hand side, when I say layer, so these are the layer of different surfaces or the different materials which we have put together to make the wall assembly. Okay, so there's a surface film resistor, there's a cement plaster, insulation puff spray, then AC block, cement plaster, and then surface film resistance. Okay, so if you see that then you have different, like we have also mentioned the different brand of it. Then there's a thickness of all the materials that in millimeters. On the in the fourth column, we have converted the thickness into meters. Then there is a thermal conductivity value for each and every surface material, and then we have calculated the resistance. And since we all know that resistance to calculate the U value, the formula is U value is inversely proportional of resistance. So what we have done is you need to divide the thickness with the thermal conductivity value, you'll get the resistance, and then you the inversely proportion of resistance is U value, and then you try and you add all the values together and you get the U value of the wall assembly. Once you get the U value of the wall assembly, then you can try and cross relate whether it is matching with the code requirements or not. So this is a very simple technique to understand whether, if it is complying with the code. If it is not complying with the code, then you try and analyze different permutation and combination, that okay, insulation की thickness बढ़ा के देखते हैं, or else wall assembly की thickness बढ़ा के देखते हैं, or else let's try and put an air cavity in between, let's try and put a cavity wall. So once you get these kind of values, once you are able to quantify all these values, then you will be able to get the answers for whether your design is right or wrong. So it's a very simple exercise that we all should do at the design when we are designing the building. Similarly, it's for roof. So if you see roof, we have green roof, insulated roof, we have cool roof system, we have reflector surface, we have solar PV. So these are the different, strategies that you can apply in roof. You can have a roof. So majority of the, the heat gains happens to the roof. So the roof assembly has to be very good in design, so that there is a way, so that we can reduce the heat ingress inside the building, because roof is the area from where you are, on which you are getting the direct solar radiation. So once you will comply the roof with the energy efficiency requirement, or you have make a roof better than that, you will be able to cut down maximum of your heat ingress inside the building. And as I'm flashing it on the screen, it has different strategies to do it. So there are different kind of roof, and there are different type of roof assemblies that you can explore, and in a similar way. So this is the screenshot which I have attached to calculate the roof assembly U factor and insulation R value requirement for the composite climate, which is there specified in the code. It is again the similar kind of calculation that we do. You need to understand the thermal conductor. You need to calculate the resistance value for each and every layer of the roof assembly, and then you need to add it all. And then you need to, once you will add it all, you will get the resistance value, and then you inversely proportionate it, and you will get the U value of the roof assembly. And that needs to be complied with the requirements specified in the code. So, and then you need to check if it is complying with the code well enough. And if it is not complying with the code, then you need to do some changes. You need to add more insulation, or you need to add a different kind of material in the roof. You need to add the surface layer resistance. So all these kind of permutation and combination you can do once you will be able to quantify the result, and once you'll be able to identify whether the roof is performing better or not. Similarly, for window, we have WWR. So, it's not like we are making the entire building with big glass windows and all. We have to have the optimization. We have to have a right WWR ratio. We have to have a right, skylight to the roof ratio, so that we should not have the, major heat coming. Because when we are saying the sunlight coming inside the building, it is not just the light coming inside, it is the light plus the heat coming inside the building. So there has to be different ways to stop the heat coming inside from the window. So it has to have a proportion, right proportion of the skylight or the window, so that we can cut down that heat. Then glazing selection. So most of us, I mean, when we practice the conventional architecture system, so conventional design process, whenever we go, like for example, if you're doing a project, so whenever you go out for material selection and all, we simply go and say, okay, this is the glass, ye aap laga do, ye wale itne thickness ka glass hame lagana hai. But actually there is a whole lot of science behind, selecting a right glass. Because if it is a very single clear pane glass with, with certain thickness, it is going to allow a heat getting inside the building. But if you have a nice spectrally selective coatings on the glass, if you have heat absorbing tints on the glass, if you have low emissivity coatings on the glass, if you have high performance glass, then you are able to reduce, you are going to, select a beautiful glass as well, but a glass which is performing better as well. So it has to be a combination of both, as I have said earlier in the previous session. It has to be a combination of both aesthetic and also the performance. Then the sun shading. So it's not like we have to design a building with a very, with a very different kind of sun shading, solar shading devices. You can design your building with a different and beautiful sunshade, as I've shown, few examples here. And I've also shown few examples earlier in the previous session. You can have combination of vertical fins, side fins. You can have operable sunscreens and all. You can have sun breakers and all, which can provide proper and adequate shading to the buildings. So again, so when we say, when we go and pick for the glass, the value, the specification that we need to see is what is the U factor and what is the solar heat gain coefficient of the glass. So we need to understand whether these two things are getting complied with the code requirements or not. Then coming to the mutual shading thing, as we have discussed earlier already. So this is just one of the examples. It's not like something, we are creating a different out of the box thing. It is a simple design, but if you see, just with some beautiful architectural intervention, we are creating nice shadow patterns as well. And it is also helping in improving the performance of the building. Similarly, Gabion walls. So we all know that the time lag of the stone and the thermal mass property of the stone, it allows us to the Trom wall and the Gabion walls and all. It can be beautifully used as solar passive strategies, and it can equally give you the right aesthetic requirements of your building design. Then the creation of buffer zones. So buffer zones create a very good role when you're designing a building. So if your building is designed in a way where your longer facade, or like the maximum the longer facade of the building is exposed towards the critical angle, like when I say critical angle, from where you're getting the maximum sun, maximum sun hours are there at that direction. So you can always try and create buffer zones. You can try and put some screens on it, so that the buffer zones will not the buffer zones will not directly allow the heat gain inside the livable spaces. So you can have some these kind of solar passive strategies while designing the building. Then light shelves. Light shelf again, like we all know that we there we have to design a window in this way, in a way where you can have the maximum utilization of daylight. But I'm sure, I mean, how many of you have actually given consideration to it? We simply design a window with overhang, that's it. But you can actually enhance your daylighting performance by adding these solar passive strategies like light shells, providing skylights, providing nice glasses, different combination of glasses, different sizes of glasses, so that you can get a entire area with which can be naturally lit and less dependent on the mechanical or let's say the artificial lighting system. Similarly, for when I said clean energy thing, clean energy or the renewable energy sources, we can always look for earth hair tunnel, and we can also look for different solar passive strategies which can improve the thermally comfortable requirement of the building. And it's not just the earth hair tunnel, because actually it requires a lot of space. And in few of my projects, I have also seen that sometimes it is not even possible. But let's try and explore. It is not just one example. There are so many different examples that we can try and explore to understand that there are different strategies that can be used to make the building thermally comfortable, and to reduce the requirement and reduce the dependency on mechanical system. So, and then finishes and indoor air quality, which is very important. Most of the time we forget that, these things are important to also, handpick. So with indoor air quality and finishes, you can actually create a nice, breathable air environment, so that there is no fungal impact, there's no health impact in the building environment. You can also always select a breathable plaster. Like here are a few of the cases and glimpse of clay based finishes to for improved indoor air quality. If you see all these tiles, those are tiles and textures that we can have with clay based finishes and all, they are equally they are cost effective also, they are reciprocating to the climate and culture also, and they are also improving the air quality inside the building. Then again, lime plaster. Lime plaster, it has been used like since we have been using this in in all our traditional and vernacular buildings, but somehow we have stopped using it. But maybe because we want to make it look in a because we are moving towards the contemporary style of construction, choosing materials and all. But if you see, we can always go back and look for some innovative material where we can have lime plaster based we have lime based internal plasters to improve the indoor air quality and equally enhancing the aesthetics of the building interiors. Then floor finishes and all. So this is one of the example I tried to put in, where this particular material is based, it is produced by, it is 100% recyclable, and it has a major component of rice husk. So 50% of the rice husk is there, and then it is there are different polymers. So we can always look for innovative materials. We can always do some research and understand what are the different kind of materials available, which are sustainable in nature, eco-friendly in nature, and also are recyclable and creating less impact or less negative impact in the environment. So just wanted to show you how the material palette could look like if you are, selecting the material for your building design and for energy efficiency requirement of the building. So next session, next topic is simulation softwares and tools. So this is very important. I mean, most of us would always, like, even when I was entering into this industry, I also wanted to know about what are the different tools that I can learn, what are the different softwares that I can learn, what actually these softwares can do and all. So these are the simulation softwares and tools that we can explore. So simulation can help you achieve the different, actually it can help you quantify the performance of the building. So earlier you might have seen, when there was no what do you call it, computer based system, it is not that simulation is the only way. Earlier also, when there was no simulation, when there was no computer based technique, we used to understand the performance of the building in a different way. Has any of you have seen this particular thing, wind tunnel air flow study? Has any of you have conducted this study, or कभी आपके लेक्चर्स में किसी कभी आप लोगों ने पढ़ाया है? So this is the way. So I remember there was this one studio when we were supposed to do this air tunnel study, where we have created the model, and then we have done this, we have created the smoke to understand how the the where the smoke is getting accumulated, how it is getting circulated, so that we can understand the air flow around, in and around the building. But these days we have a simple, but it was like a lot of effort to set up a system like this and then analyze it and all. But now we have simple system which we can use it.
Hello, ma'am, is everything okay? We cannot hear your voice, ma'am. Participants, I think ma'am has some network issue. Let us
Yeah,
wait for a moment
Nishta,
for her.
just 1 second. I think my other system has got disconnected. I'll just quickly connect it.
Yeah, sure, ma'am, no problem. Participants, can you all show can you all send a reaction for this session that was going on until ma'am is back? If you liked the session taken by ma'am, you can just react with a thumbs up.
Nishta, can you see my screen?
Yes, ma'am, it's visible.
Sorry about that.
No problem, ma'am.
Okay, so just let me know till which slide it was audible. Okay, can I start with this slide?
Yes, ma'am.
Okay, great. Yeah, so what I was telling is that earlier the building used to be designed with the intent of providing structural strength and climate responsiveness for safety and comfort of the occupants. But now the buildings today that we design are with electromechanical equipment for provision of the services and comfort of the occupant. And thus the present day buildings became platform for stakeholders with vivid disciplines for design and operations. So earlier when we say that okay ghar banana hai ya building banani hai, तो okay ठीक है, just let's get the contractor and the architects involved. But now these days it has become like a comprehensive project. Like every stakeholder has to be aligned with the design, like architects, MEP consultants, as I keep repeating this, because to make this thing concrete in our mind, that it is not a solo act now. It has become where all the stakeholders have to be aligned at the right time, at the right stage, so that there is no, there's no bad design kind of thing. Like there's no issue. There's no sorry, I mean, there's no right design or a wrong design thing. But yeah, when you have to, if all the stakeholders are involved at the right stage, you will not be facing any issues where you get a shock. Arey, ye kya hua? Like, this is not I was expecting out of my design. But to just additionally integrate the energy efficiency thing. So, oh, this is what I get. No, this is not the case. If we have all the people at the right stage, we can all brainstorm together. We can have a design share it, so that we can integrate all the services as well together at the right stage of mind. So when we do building energy simulation, so building has different components. So building could be considered as high performing when longer duration of comfortable building conditions are provided with less or no use of energy sources. So the parameters related to climate, build form, envelope insulation levels, occupants behavior, efficiency of the appliances and equipment play a pivotal role in providing comfortable conditions in the build spaces. So yeah. So when we do building energy simulation, the advancement, so we have, like there is the advancements in today's world where we have, multiple options for build form, envelope and appliances to choose upon. And thus decision making process becomes critical for any building design or for any building design stakeholders to choose the effective combination. So, and without assessment, it is very much restricted. So if you will not be able to analyze or assess what exactly what is the right combination, then it is very difficult for you to understand what should be the right combination. And therefore, these simulation, or the, let's say, not the simulation, these, what do you call it, computer based solutions give us the options to select the right solution for the building or the right combination for the building. When we do building energy simulation, we consider two things: the thermal aspect, the lighting aspect. For lighting, we consider the day lighting and the electrical lighting aspect. For for thermal analysis, we select the components, building components and different systems. Like and then once you will have all these things in place, once you have all these things in place, you will be able to select the right combination for any particular building design. Okay. So coming to the next slide. So when we say building energy simulation tool groups, so earlier there was this text based input. Then we have got this graphical user interface based input solutions. Then now in today's analysis and assessment that we do can be an integrated input, where you integrate the graphical user interface as well, and plus you can also use the virtual programming interface as well. So maybe you might have heard a lot that with all these advancements in the technologies, with all these programming advancements in the technologies, we are improvising our efforts in terms of understanding and analyzing the building performance of the building performance of any construction style or typology of the building. So if you see the text-based input, earlier the building energy simulation tools comprise engines with mathematical models that require inputs to simulate the thermal as well as lighting performance of the building. And you might have heard the popular engines like Energy Plus have text-based input system. So you need to, where a typical syntax is providing each input existing along with extension format. So you have all the inputs, you put everything, and then there is a mathematical model for it. There's a mathematical syntax for it, and then you get the result for multiple zones. But then with the advancement, you have the graphical user interface that allows you to address constraints that you will face in text input based system. The modeling interface today help the users to input component wise details. Like earlier we had just has the option to input the values and all, but now we can also give the inputs based on let's say window wise thermal properties, let's say room wise occupancy schedule. We can also give zone wise equipment usage and so on. Then with GUI plus VPI integrated input, we have this option. Like so you might have also learned, there's a software you might have also learned. Just write yes or no in the chat bar. Have you heard of Rhino and Grasshopper software? Yes, good. So basically, we have in the Rhino and Grasshopper software, we have different plugins which so where you can do all these kind of analysis and assessment. So again, as I've mentioned earlier, we have already been doing and practicing these analysis and assessments. It's all about moving or let's say taking a leap toward assessing the performance aesthetics of the building. So earlier, I remember rhinoceros when we used to just design the building, and we get the output, like the design output of from the Rhino software. But then using different plugins, software plugins and all, you will be actually able to understand, okay, now how this is performing. Okay, and these platforms are not just allowing energy simulation, but also allowing us to do the environmental simulation as well, which are interlinked to building energy performance. And for instance, let's say sun path and wind analysis for deducing fenestration position, and design in building that alter the comfort conditions, or let's say energy use in natural ventilation or mixed mode ventilation. So all these kind of analysis we can do through these kind of software. So just understanding what are the inputs that we give for the energy simulation tool, and what kind of output that we receive from the energy simulation tool. So you input weather data, relative humidity, wind speed, etc. Then you give input for building geometry, construction. So left hand side you see all the inputs are given, like internal load, system and control. Then you run the energy simulation, and what are the output that you get from the simulation? You get energy consumption of each end use, lighting, cooling, etc. You get comfort results, zone temperature, hours and comfort, hours of comfort, etc. Then you also get breakup of cooling and heating load, related to building envelope, internal, etc. Then cooling and heating system size for peak load breakup at the zone level. Because earlier we used to, we have this, when you are having this text-based input, as I've mentioned, you don't get these kind of input, but now you can also, get the breakup of zone level. Like, okay, this is a particular zone, like let's say bedroom hai, toilet hai, ya kitchen hai, ya living room hai. So you get the breakup for all that load calculation. Then for lighting, yeah, for lighting, you can give input for scene geometry, surrounding landscape, ground reflectance, optical material properties, status of artificial lighting, status of shading devices. Then you can, select the area of interest, viewpoint, grid of sensor points. Then you can also select the space usages. Then you can also select the sky model, whether it is, based on the weather data, date, time, latitude, longitude, sky condition, whether it is overcast or clear. And these kind of analysis you can do in a software called DaySim. Or let's say that there are different softwares as well. So this I'll give taken, I'm giving an example. Yes, that DaySim can be one simulation software that you can use. So based on the experience sharing, so there are different simple tools and with which you can do the climate analysis, like climate consultant, therm, window, confin. Then you have DaySim and groundhog for daylight analysis. You have relux, dilux, evo for artificial lighting analysis. You have red screen for renewable energy, renewable system analysis. You have NVMet for urban environmental analysis. Then for optimization analysis, you have GenOp. You have for CFD analysis, which CFD that we do for wind flow and all. So this you can do it in Fluent or SC Stream. So these are the different softwares that you can use. Then for building performance tool, for just for thermal performance analysis, you can do it in Equest, Ansys, Aqua. For thermal performance plus lighting analysis, you can use the Autodesk tool Ecotect or Open Studio. Though Ecotect is not much used today in the industry, but Open Studio you can use. Then thermal performance plus lighting plus CFD analysis, you can do it in a design builder or IES software. These are the integrated softwares. But then coming to the next generation software, as I've mentioned, you can do, like, for example, Rhino Grasshopper with, the Ladybug and Honeybee plugin. You can use you can do different kind of analysis for visualizing the weather data, analyzing the weather data, analyzing the geometry of the site, estimating the renewables. Then with then you can also, like, if you see here, it is so integrated that you can do daylighting, you can do thermal performance, you can do solar radiance analysis, and everything together in one integrated software. So this is the canvas of what kind of analysis you do with all these simulation software. So I'm going to share this link. I'm just wanted to show that, these are the different web links and software that you can download from these links. I'm going to copy this in the chat box for your reference. Just in case if you want, let me know yes or no. I can share these links with you so that you can just go understand and download these kind of tools and software. So we are at the end of the presentation, and with which I would just like to, just show last few slides for sun path diagram, because we have talked about it a lot. So do you know, just wanted to know, like, you all know how to read the sun path diagram? Yes or no? Yeah. So I don't know, but still I'm gonna tell you. Even if you're not gonna answer, I'm gonna tell you. So basically, in the sun path diagram, if you see these lines, these are the day lines which show the summer solstice, 21st June. This particular dotted line in the middle shows the equinox, and then 21st January, this particular line, the third line in dotted shows the winter solstice. Then these are the lines which are the hour lines, which show at which hour we are reading the sun path. This is sorry, I forgot to mention this sun path is for New Delhi, so for which I'm giving the reference. Then these circular lines talk about these are the altitude lines. Okay, so these are the altitude lines which tells you, at which altitude the sun is. So if you see, the Tropic of Cancer goes from 23.43 degrees north. So if you see at Amritsar, your sun path diagram will look like this, slightly, towards are you able to see my screen? Because it seems like my screen is stuck. Yeah. So if you see your sun path diagram with latitude 31.4 degrees north will look like this. Then your sun path diagram for Bhopal, which is very near to the central line, so with latitude 23.3 degrees north will look will slightly be shifting towards the north. And then Chennai, if you see your the sun path diagram will be like this. Okay. And once, if you see, so this is for India. So if you see the difference, if I take the sun path diagram from Melbourne, the sun path diagram will be, so Melbourne is minus 37.8 degrees. So you need to understand, like, what is the difference between the sun path and how it is going to shift with the different latitude and longitude. So with this, I'm going to end my presentation, and I hope it has addressed your queries to how to integrate your climatology study with applied climatology. And over to you, Nishtha. And
Thank
again,
you.
I'm gonna copy the links before we end this presentation so that the chat box will not appear later. I'm gonna copy all these links for all of you to refer, and just let me know if you want to know anything more about about the softwares, or if you have any query related to it, I'll be happy to help.
Thank you, ma'am. Thank you so much. It was a really detailed presentation. I could see that there were so many slides in the presentation while you were presenting it to us. But you covered everything very nicely. A lot of things were clear for us. For example, I'll just give the smallest example. Like you just talked about the sun path. We use sun path so many times, but maybe not all of us know how to read it properly or entirely. So you gave many such examples throughout your presentation, both in the first session and in the second session. And it was really helpful for all of us, and we learned so many new things. You also showed us some new perspective uh, for looking at the same thing, but from a different angle. And especially, you said that it might have cleared, it definitely cleared a lot of our doubts on how to engage students in such design studios where climatology is not just something that they have studied as an additional subject, but is very much a part of their design studio. Now, I would like to open the floor for all the members, all the participants who are at the moment here in this faculty development program. If you have any questions for ma'am, you can please ask now.
Just want to add one more thing. If considering the time, if we are not able to address all the questions, I will also you can also take my email ID from Nishta, and you can get in touch with me. And you can also take the number if any point of time you think that you need any suggestion, not suggestion, I'm not very good, I'm not saying that I'm good with giving suggestions and all, but yeah, any queries if you will have to with related to this particular session or related to climate responsiveness or energy efficiency, I'll be there to answer those queries.
Any questions from anyone or any comments, anything, any feedback also? It's most welcome.
I'm gonna start a quiz again if nobody asks the question.
Okay, with that, I think, ma'am, we come to the end of today's session. It was really great, and honestly, it was the most interactive session in all these 4 days because the way you asked questions in between, you also conducted a short quiz, and it was related to all the topics that you had already discussed in your first session. And basically, it was very interactive. People were actually listening to you. They were also dropping comments simultaneously while you were teaching things. They were also giving answers. So I guess everyone was very attentive throughout the presentation, and we all have learned so much today. I would especially like to thank you because you dedicated so much of your time today for this faculty development program, and it was truly a good learning experience for all of us. Thank you.
Then bye everyone. Nishna, maybe whenever if anyone wants to get in touch, you can share my email ID or contact number, and maybe we can, if there is, I just hope that I'll be able to address their queries in future. Thank you so much. Bye bye. And thanks to Amity University for giving me this opportunity for being part of this faculty development program. I really enjoyed it because most of the time I feel that participants are not listening, and sometimes it becomes very mathematical, technical, too technical for people to actually get engaged, to engage all the participants during the session. But I'm happy that they are all responding, and I really look forward for many such programs in future. Thank you.
Surely, ma'am. We also look forward to many such programs. Hopefully, we will be able to meet you offline next time, and we can also organize such events for the students as well.
Yes,
So
yes.
it will be very useful for them too. Ma'am, people are also leaving some very positive remarks in the chat box for you.
Thank you, Payal. Thank you. Look forward to get in touch with you all. Bye-bye.
Ma'am, if anyone asks, I'll share your email ID or contact information.
Yes,
Thank
yes.
you so much, ma'am. Thank you for joining us today. Have a very good day.
Thank you. Bye-bye. Bye, everyone.
I request all participants to stay back for a moment. Participants, as you know, that we were given an assignment, and that assignment needs to be assessed tomorrow. There will be a feedback session for the assignments that we are working on. So I also need to collect these assignments in one place, and I need to share them with ma'am. Ma'am will go through these assignments by today evening or tonight. And tomorrow, what we have to do is we all come back, and tomorrow's session is all about feedback and evaluation. And while ma'am will give feedback to the assignments that we have done, she will also teach us on how to evaluate these assignments when we give them to our students. So it's going to be a very good practical learning opportunity for all of us. Now, I really hope that you all have completed your assignments till now. I have received 2-3 mails. There are some individuals or group of people who have completed completed their assignment and they have already sent it to me on the email. So I was really happy to see that you all are so enthusiastic and you have already completed it. But still, if you have not, please try to complete it by tonight maximum, so that we can talk about them tomorrow in tomorrow's first session. Also, participants, tomorrow when you come, either in the first session or the second session, in one of these two sessions, you have to present your assignment that you have worked on. Now, this presentation can be in any possible way. If you have drawn something on a piece of paper, you can also take a picture and you can just share it on your screen. If you have drawn something digitally, then also you can share your screen if you have made a model or something. If you want to share pictures, you can do that, or you can just switch your camera on and you can show it to us in the class and you can talk about it. When you present your assignment, you just have to talk about it. Just like we take very brief presentations from students, just like that. For like a minute or two, you just have to speak about what was the topic that you chose, what did you work on, what was your concept behind it, and what was your idea behind what you did, what did you conclude from it. So basically, very briefly, you just have to explain the work that you have done, and then ma'am will give her feedback on it and she'll further teach us on how to evaluate. So that is what we are going to do tomorrow. So I am thinking of sharing a drive link where we all can upload our assignments together. I'll share these assignments with ma'am so that she can also look at them once before coming to tomorrow's session. So will that be okay for everyone? Will that be comfortable for everyone? Please let me know, participants. I'm waiting for your approval. If you all agree, I'll share the drive link in half an hour. I have some urgent matter to look at into. In another half an hour, I'll share a drive link with you all. I'll try if I can share it earlier also. And you all can upload your assignments in that drive link. Please make sure that you upload your assignment with your name. If 2 or 3 people also have worked on that assignment, please make sure that the 2 or 3 names are there in the image name that you're uploading, or make a folder and upload it with your name so that we can understand that whose assignment is it. Okay, I guess everyone agrees. I'll share a link or Google Drive link in some time. Please make sure that you all upload your assignments by tonight. Okay, participants, thank you so much for joining us today. It was a great session by Anubha ma'am. And tomorrow will be the last day. Make sure that all of you are present tomorrow as it is the last day. And one of the most interesting sessions is going to happen tomorrow by Pradnya ma'am. So let's come back with all our colorful and vibrant and thoughtful assignments that we are working on. And let us learn something new. It will be the last day, so we'll also take a nice group picture with everyone. Thank you all for joining. If you have anything to say, any feedback, query, question, please feel free to reach out to me. You can also contact me on WhatsApp through direct message, or you can drop your messages in the WhatsApp group. Thank you. Have a good day.